Everyone. Welcome back after the Eid break. Before the break, we were discussing about steady state, steady flow systems. And now we will continue our discussion on steady state, steady flow systems by talking about a few more devices which are of various important uses around us. So let's talk about turbines and compressors. All right. So starting with a turbine. So turbine is any device that is basically used to drive an electric generator and gives out a work output, right? And this is or a power output. So turbine is very commonly used in a steam power plant, a gas turbine, or even a hydroelectric power plant. Now, when we talk about a steam power plant or a gas power plant, the role of a turbine is to actually give out the work output, and it basically converts the high enthalpy of the incoming fluid, which comes in at state one, and it converts that into the work output, right? So the concept is very simple. A turbine, by definition, is simply a device through which a fluid enters, which basically comes in at high enthalpy, right? When we talk about steam or gas turbine, and it uses this high enthalpy to do work against the turbine blades, which basically rotate the shaft, right? You have the rotation of the shaft, and this rotation of the shaft turns the electric generator to produce the electric work or the work that we are interested in, shaft work or electric work, whatever you are interested in, right? So simply, whenever you hear about a turbine, you should remember that the role of a turbine is to produce work output. Okay, this is what the role of a turbine is. You can say produce work output, or you can also say produce power output, because power is simply the rate of work, nothing else. All right. Now, when we talk about a turbine, we again need to go back and look at how the energy balance would look like. Okay, so this is the general formula for energy balance. And when we are dealing with a turbine, normally we don't really consider the heat coming into the surroundings. I mean, heat coming into the turbine, because there's absolutely uh, no heat that comes into the turbine, right? We don't heat up the turbine. Okay, so heat Qn is always zero. Now, there's also never any work input into the turbine, because the turbine by definition produces work output. So work input into the turbine is also zero. Now, if you're considering the example that I'm showing here, this is a single inlet and a single exit turbine, which basically means that I don't need to do the summation. I just need to talk about the mass flow rate at the inlet, which is just one inlet, times the associated energy, which is in terms of enthalpy plus kinetic and potential energy. Same way, I don't need the summation sign at the exit. Okay. Now, what all is important from the other terms? Well, from here, in general, we can neglect the changes in kinetic energy, which basically means that V in and V out cancel out each other. Same way we can neglect the changes in potential energy, right? So which basically means that the potential energy part Gzn cancels out with Gz out. So what we are left with is a very simple um, energy balance equation, which gives us m dot h1, which is the only term that is left in here, right, is equal to work output, which is the main role of a turbine, which is produce work output. This is the simple reason why we build a turbine, right? The critical work output plus any heat loss to the surroundings, which can happen. Okay, it's usually zero, but there can be heat loss to the surroundings, plus m dot h2 or m dot h out, right? Which is simply the enthalpy at the exit. So essentially, if you look at the energy balance, what we are seeing is very simple. The mass times the enthalpy that comes in, which is the energy that comes in, is basically used to produce a power output, which is W dot here, and the remaining energy, or the part that does not gets converted to work, it goes out as m dot h2, which of course is a much lower enthalpy than the enthalpy of the inlet. So essentially, you can say that the work output is equal to the difference between the inlet and the exit enthalpies, right? And this is a very simple energy balance for a single inlet, single exit turbine, let's say with some heat loss to the surroundings. Now, if you don't have any heat loss to the surroundings, you can, of course, make this Q out also zero. Okay. Now, let's consider another example here where we don't have a single inlet, single exit turbine, but we have a single inlet. Okay. But double exit turbine. a turbine with two exits. All right. So what we can see is that some amount of energy is coming here at state one. Some amount is going out at state two. Some amount is going out at state three. And of course, uh, some amount of work output is being produced or power output is being produced. And there's also some heat loss to the surroundings. Now, the energy balance for this sort of a turbine with one inlet and two exits would look very similar. Again, the way to obtain it is to start from this general formula for energy balance. Okay, so if you look at it, what we can simply say is that, of course, there's no Qn, right? So Qn goes down to zero. There's no work input into the system. A turbine does not take any work input. And this is a single inlet. Okay, the usual stuff about kinetic and potential energy, the changes we can say are they're negligible. So these two terms also gets cancelled out. So what we are dealing with now is m dot 1, right? H1, which is the mass flow rate and the enthalpy at state one, which is the inlet. This is equal to a lot of things. This is equal to the heat that is getting transferred from to the surroundings. So that's Q dot out plus, of course, the work output, right? W dot out plus some amount of enthalpy which goes out at state two. So it's m dot 2 h2. Remember, we need to take into account the mass flow rate at which it's going. So the mass flow rate at state 2 is very important. So plus m dot 2 h2 plus again the mass flow rate and the associated enthalpy that's going out at state 3. So m dot 3 h3. Now, how did we get these m dot 2 h2 plus m dot 3 h3 term? Simply by looking at the summation of this. So summation of all the outlets where you take the mass flow rate of that particular outlet times its enthalpy. So m mass flow rate at outlet 2 times enthalpy at outlet 2. Mass flow rate at enthalpy outlet 3 times enthalpy at outlet 3. This is exactly what we're doing. Overall, we say that the changes in kinetic and potential energies are zero. So these get cancelled out, and this is how the energy balance would look like. So remember, every time you're trying to write an energy balance for a very simple turbine, single inlet, single exit turbine, you can simply start off with this formula, if you remember, right? Otherwise, the best thing is to basically start with this general energy balance formulation and narrow it down to whatever you want. And again, I will be providing this general formula for energy balance will be provided. Okay, but this formula, which is very specific to a single inlet, single exit turbine, will not be provided. You have to you should know how to derive it from the general formula, or you can remember it. It's your choice. Okay, same way, if I give you a turbine with single inlet, two exits, you should know how to derive it from the general formula. Okay, so this is all about turbines. We will solve problems on turbines, of course, to give you a more understanding of how this all works out. Okay, so that's for the turbine. Now, when we talk about compressors, well, compressors are also called by some other names, such as pumps and fans. Well, when we talk about compressors in general, or even pumps, the whole purpose of these devices is to increase the pressure of a fluid, right? The whole purpose is simply to increase the pressure, and therefore you need to supply some work in to these devices. Okay, so they take a work input. Okay. In a compressor, there is no work output. There is work input. On the other hand, for a turbine, there is no work input. There is work output. Okay, so the role of a compressor is simply to take some amount of work input and use it to increase pressure of the fluid. Okay, so whether we talk about a compressor or a pump, the rule is very simple. What we want to do is to increase the pressure, which would in turn increase the enthalpy as well, right? And it would show up in the energy balance. Okay, so this is simply why we build a compressor. So if you talk about a very simple compressor, which is single inlet, single exit, like the one shown here, well, the energy balance for such a compressor would turn out to be as shown here, Wn, which is the work input, plus m dot h1, which is the mass times the enthalpy at the inlet, would be equal to m dot h2, which is the mass times enthalpy at the exit, right? And h2 would be greater than h1. And this is basically the entire reason why we build a compressor or we build a pump to increase this enthalpy or to increase the pressure, right? Which will show up as increase in enthalpy for a lot of fluids. And at the same time, there could be some heat loss to the surroundings. Now, heat loss to the surroundings This is undesired. This is not uh, actually, this is some sort of a loss, right? It's not something you want. It just happens if the compressor is not very well insulated. Okay, ideally you want Q out to be zero, but sometimes you cannot make Q out to be zero. It can be really small quantities, or it can be relatively large if the compressor is not insulated. So now again, this formula, the specific formula for a compressor will not be provided. You should know how to derive it from the general formula. Okay, very quickly, the way you can derive it from the general formula is simple. You got to remember what a compressor is for. In a compressor, we don't provide any heat input, right? It has nothing to do with heat input. So heat input is zero. Of course, we provide work input. So the work input into the compressor should be there. If you're talking about a single inlet, single exit compressor, there's no need of summation. So summation signs cancelled out. It's basically mass flow rate at the inlet was state 1, m dot 1 times enthalpy at the inlet, h1, right? What is what we have written here, plus the changes in plus kinetic and potential energy. Now we always, in general, if velocity is not provided, or if there's no information on potential energy, in general, we can assume the changes in kinetic energy and potential energy to be zero for a turbine and a compressor. Okay, but if the question gives you some velocity, you got to make use of it. But again, the changes are really, really small as compared to all other things. So in general, these terms would cancel out. And again, there could be some amount of heat loss to the surroundings, which will show up as Q out. There is, of course, no work output in a compressor, right? A compressor does not produce any work output. So work output is zero plus m dot out times enthalpy at the exit, or m times h2. Now here, when we are talking about a single inlet and a single exit device, I don't talk about M1 or M2 simply because whatever comes in is going out, right? It's a steady state, steady flow system. So the change in mass flow rate is zero, which basically means that M dot is equal to M2 is simply equal to M dot, right? So M dot 1 is equal to M dot 2 because what comes in has to go out, it's not getting stored. So you can also just write it as m dot, which this is how we write it here, okay? Or in this case, okay, we don't have to write 1 or 2 because, well, m dot 1 is exactly equal to m dot 2. That happens when you're dealing with a steady single inlet, single exit systems. If you're dealing with a system like here, where you have one inlet, two exits, then you have to apply mass balance, which basically means that whatever is coming in is equal to what's going on. So m dot n is equal to m dot out, or you can write m dot 1 here is equal to m dot 2 plus m dot 3. Okay, so this is essentially how you deal with. So this is all about turbines and compressors. I'll also talk about what are the general ways in which turbines and compressors are used, and then we'll go ahead and solve a couple of problems based on that. Okay, so just to recap, here what I've shown you are very simple, are simple versions of turbines and compressors, single inlet, single exit. Uh, these are extremely common, but we also have more complicated versions like the one shown here. Or essentially, when we talk about practical applications, we don't just have one turbine, but we tend to have more than one turbine in series, right? So like the one shown here, you have turbine one and turbine two, right? So these you have two turbines which decrease the overall pressure in steps. P1 to P2 is a reduction, and then P3 to P4 is another reduction. So they produce the total power produced would be the power produced from turbine one plus the one from turbine two. Same way when we talk about compression process, which is increasing the pressure, sometimes it makes more sense to do the compression process in two steps, right? And have a compressor, have two compressors in series, like what is shown here in this figure. And in between the two compressors, you sort of cool it down. Okay, why does it make sense to cool it down? Well, it'll all become more clear when we go and talk about this in more detail to in sometime in chapter 5 or 6. But the whole purpose of showing this is to just to make you aware of how is it used in practical applications, right? If you visit any power plant for the Saudi Electric Company, Aramco, or any, or the Saudi water, the Saudi desalination company, right? Saline water conversion company. You will see very similar versions of them, right? You'll see multiple turbines in, or at least two turbines in series like the one shown here, or multiple compressors in series like the one shown here. Okay, so this is simply the purpose of showing you these figures. Now let's go ahead and let's solve a problem for a turbine first. Okay, so here we are dealing with a turbine, and here it says steam enters a turbine which is operating at steady state, and it's entering the turbine with a mass flow rate of 4,600 kilogram per hour. So the mass flow rate is provided to us. Okay. Now the turbine, it develops a power output of 1,000 kilowatt. The turbine power output is also provided, and as I told you, the whole purpose of building a turbine or whole purpose of purchasing a turbine is because we are interested in generating this power output, right? Which is 1,000 kilowatt. Now at the inlet of the turbine, the pressure is 6 megapascal and the temperature is 400 degrees Celsius. Velocity is 10 meter per second. Okay, so these are the conditions at the inlet. At the exit, we have the pressure. Again, pressure is 10 kilopascal. You can see a huge reduction in pressure. The quality is 90%. The quality is provided along with pressure, so which means that we're dealing with a saturated mixture, and you exactly know how to get properties for the saturated mixtures. And the velocity at the exit is 30 meter per second, slight increase in velocity. Okay. Now for this information that is given to us, we need to calculate the rate of heat transfer between the turbine and the surroundings in kilowatt. So it seems there is some heat loss to the surroundings, Q dot out. And all we need to do here is to determine how much is that. Okay. So let's write down the information here. The objective is to determine the Q dot, the heat transfer. And based on our understanding of the system, we can say that this is probably heat lost from the turbine to the surrounding. So it's Q dot out, right? It's not N. Okay. This is something that we can have from our understanding. Again, you can say that, okay, maybe heat is coming into the turbine, and you can calculate, you can apply energy balance and do all the calculations, and then you'll figure out based on what sign we get. Okay. So the objective is to determine the heat transfer, in fact, the rate of heat transfer, Q dot, not just Q. And the system that we're dealing with is an open system, of course, it's not a closed system. We're dealing with a steam turbine with one inlet and one exit, okay, because that's the kind of information that was provided to us. And we were also provided this rather simple sketch. Okay, so let's note down the inlet and the exit information in the form of a table like we always do. So this is the information available at the inlet: pressure, temperature, mass flow rate, and velocity. Okay, same way you have information at the exit, which is pressure, quality. And since we are dealing with a steady state steady flow device, which is a turbine, and all turbines are steady flow devices by default. So we can say that since we're dealing with a single inlet, single exit turbine, the mass flow rate at the exit should exactly be equal to the mass flow rate at the inlet, and it's just the value that is given to us. Okay, the velocity at state 2 is 30 meter per second, and it's undergoing a steady state steady flow process as it goes from inlet to outlet. Okay, so now the way to solve this is actually very simple. All we need to do is to apply the energy balance. All right, and this is the general energy balance here. Qn minus work out is equal to summation of M out times the relevant energy minus Mn times the relevant energy. Now again, we are dealing with the turbine, so we can always consider changes in kinetic energy to be 0 and changes in potential energy to be 0 as well. Okay. However, in this case, the velocity is provided both at the inlet and at the exit. So this time we will not go ahead with this assumption. We will actually go ahead and calculate. We'll calculate these terms, the kinetic energy terms, right? The velocity inlet and velocity outlet, and see how much of a contribution does it. Okay. We will, however, go ahead with the assumption of changes in potential energy is 0 because no information is given to us. So we can safely assume that these two terms cancel out. We're not dealing with multiple inlets, so it's just a single inlet, single exit system. And so we can cancel out the relevant terms, and we can write down a more simpler version as Qn minus workout is equal to m dot, right? I'm just writing m dot. I'm not writing m dot 1 or m dot 2 because they are exactly the same, times h out as state 2. So H2, okay, plus V2 square by 2 minus H1, Hn is H1 plus V1 square by 2. Okay, so this is simply what we have here. All right. Now I can rearrange this basically to be in the form of Qn, which is what we want to determine Q, right? So Qn could be written as work output plus m dot h2 minus h1 plus v2 square minus v1 square by 2. Okay, so here we know m dot, it's given in the question. H2 and H1 can be determined because we have enough information. For state 1, we have pressure and temperature. The inlet for a turbine is almost in all cases superheated vapor. Okay, it's really hot. So we can just go to table A4 and make sure that it is the case actually. Okay. So we have enough information, pressure and temperature are given, so we can determine the state. And for the exit, we have pressure and quality, so we know exactly what we're talking about. Again, we can determine the state and get H2 as well. Okay, well, although we need to go and do that. Velocities have been provided. We can plug those numbers in, but we got to be careful in how we do that while taking care of the units. The work output is provided to us already. The rate of work output is provided to us. And what we want is the rate of heat transfer. Now, note that here I'm taking Qn. Okay, so I'm just assuming that maybe heat is coming in. I can go with any assumption. All I need to do is I need to keep it properly. If I'm assuming Qn, then this is where it should be in the equation, right? So again, throughout the once we do the calculation, if we get a negative value for Qn, it simply means that the heat was actually going in the opposite direction. Okay, so we'll see what happens. So this is how you can write it down. And now we need to go and get H1 and H2. H1, as I said, it's most likely superheated vapor. So you can go to table A4 and you will actually find that this is superheated vapor. This is the enthalpy at state 1 corresponding to a pressure of 6 MPa and a temperature 400 degrees Celsius. State 2, we obviously know it's saturated mixture. So you'll have to go to the saturated pressure table, which is table A3. And there we got to make use of this formula, HF plus X2 times HFG, as you always know, for determining the enthalpy for this mixture. Okay, so you plug in these numbers here and we get the enthalpy at state 2. Now we have H1, and H2 already. Mass flow rate has been provided to us, 4,600 kilogram per hour, but we need to convert this into kilogram per second for consistency. So this will be 4,600 divided by 3,600 kilogram per second. 3,600 is simply hour to second conversion. You have 3,600 seconds in an hour. So that's the conversion that we will need to do. And when we are dealing with velocities, we got to remember that here v square by 2 in terms of units is meter square per second square, which essentially is equivalent to joule per kilogram. Okay, but all other things that we have, like the enthalpies and other stuff, it's provided in terms of kilojoule per kilogram. So we're going to divide this v square by 2 by 1,000, right? V square unit divided by 1,000, so that this kilojoule joule per kilogram becomes kilojoule per kilogram. Okay, and that's exactly what we will do in the next slide. This is something that we have discussed before, so it's something that you are expected to remember. So here Q minus W, Qn minus W out. W out, the power output is 1,000 kilowatt, is equal to m dot 4,600 by 3,600 times H2 minus H1. We found these from the property tables. Table A3 and table A4 plus V square by 2. Remember, I said meter square per second square is joule per kilogram, but this one is in kilojoule per kilogram. So we divide this V square by 1,000 here just to convert this joule per kilogram to kilojoule per kilogram. Okay, that's what we are doing as we did before. And then when you plug in these, when you do the math, this is what it comes out to be. This difference between H2 and H1 is 831.8. The velocity difference is so small as just 0.4, right? So you can see the changes in kinetic energy, even if they exist, they're so small that you could almost neglect them. But of course, we are not neglecting them now. We're going to calculate it as it is. So when you calculate, do the math, the Q dot N, it comes out to be minus 62.3 kilowatt, which basically means that heat is not coming in, but it's actually going out. So Q dot out is actually equal to 62.3 kilowatt. Okay, so this is the amount of heat that is rejected from the turbine to the surroundings. Now, what if you neglected kinetic energy changes? What if we said delta K is 0? So if we neglected kinetic energy changes for this particular problem, then the heat transfer or the Qn would come out to be minus 62.9 kilowatt. Okay, or Q out would be 62.9 kilowatt. And as you can see, the difference between these two numbers is not so much. So this is the reason why we, in general, why we basically go ahead and neglect kinetic energy changes, because they're really, really small as compared to all other changes that we need to consider within the system. All right, so that's about it for the problem on the turbine. If you have any questions, please feel free to get back to me next week and we can discuss this in more detail. Okay, so now let's go ahead and talk about a problem on a compressor. And here I'm going to use a different fluid. In the previous example, we made use of the tables to solve the problem. But here we're going to consider air, which is an ideal gas, and we're going to apply and we're going to solve a problem on a compressor, right? So just to give you a good variety of problems to understand how things work out. So let's see what we have been provided here. We said it says air with enters a compressor, which is operating at a steady state, and it enters at a pressure of 100 kilopascal, a temperature of 290 Kelvin, and a velocity of 6 meter per second through an inlet with an area of 0.1 meter square. So we have the inlet area provided to us, we have the inlet velocity provided to us, and we have pressure and temperature. Okay. Uh, Now at the exit, the pressure is provided as 700 kilopascal. And as you can see, the pressure at the exit, P2, is greater than P1. And as I said before in the introduction for the compressor, the whole purpose why we have a compressor is to increase the pressure P2, right? So P2 has to be greater than P1. If P2 is not greater than P1, then you know the compressor is of no use. We don't make the compressor then. Okay, so at the exit, the pressure is higher at 700 kilopascal, and correspondingly, the temperature is also higher. It's 450 Kelvin. Okay, and the velocity is 2 meter per second. Okay. Now, heat transfer from the compressor to its surroundings, it occurs at a rate of 180 kilojoule per minute. So heat Q dot out, right, is 180 kilojoule per minute. It is not negligible. Or you can say that Q dot CV is minus 180 kilojoule per minute, which basically simply means that Q dot N is minus 180 kilojoule per minute, nothing else. Okay. So this is the information provided to us. Now we need to employ the ideal gas model so we can treat air as an ideal gas. And here we need to treat it as an ideal gas with variable specific heat. And doing this, we need to calculate the power input to the compressor in kilowatt. Okay, so the whole objective of this problem is to actually determine the power input to the compressor. All right, so as we said, the role of a compressor is to increase the pressure, and it does so by taking in some work input. Okay, and that's exactly what we need to determine. Now, the system that we are dealing with again is an open system, but this time we are dealing with an ideal gas, which is air, and we're going to deal with we're going to treat as to have variable specific heat, which is basically the most exact solution. Okay, and it has single inlet, single exit based on the figure and based on the information given in the question. So now let's write down the information that's provided to us. The inlet pressure is given, temperature is given, the area at the inlet is also given, and the velocity is given. Okay, so there is a lot of information provided to us, but you can see that we have not been given the mass flow rate. Okay, the mass flow rate at the inlet or the exit is not provided to us. On the other hand, we have been given the area and the velocity. So there's the reason for that, and we'll see how we make use of this information. At the outlet, we have been provided again the pressure and the temperature, which is very useful, which completely defines the state of the system, especially since we are dealing with an ideal gas. All we need is temperature to fix enthalpies and internal energies and so on. Okay. It's a steady state, steady flow system with one inlet, one exit based on what is given in the question. So we can simply go ahead and say that mass flow rate at the exit is exactly equal to the mass flow rate at the inlet, and it's equal to m dot. And the velocity at the exit is also provided to us. So remember, when we're dealing with a compressor or a turbine, in general, we can neglect the changes in potential energy and we can set them to zero. Same way, we can neglect the changes in kinetic energy and set them to zero. However, when velocities are provided to you in the question, you got to make use of this velocity and calculate the kinetic energy changes. Okay. Again, you will find out the contribution of kinetic energy change within the energy balance is very small, which is why we basically neglect the changes in the first place. Okay. Now, of course, the system that we're dealing with is undergoing a steady state, steady flow process, and that is what has been provided to us in the question. So now again, let's start with the general energy balance. Okay, this is the sort of energy balance that is given in the question. As we were discussing about the energy balance, there are two forms. We can go back and look at the two forms, but we can go ahead with any form that you prefer. Okay, so this form basically involves Qn minus work output is equal to the changes in the uh, enthalpy and the associated energy for the fluid at the exit minus fluid at the end. Okay. Again, changes in potential energy are zero, so we cancel them out. We are also dealing with a single inlet, single exit system, so we can cancel out the summation sign, which basically leaves us with Qn minus work out is equal to m dot times h2 plus v2 squared by 2 minus h1 plus v1 squared by 2. This is exactly the same equation that we had in the previous example. Of course, the fluid was different, but basically you start with the same equation, similar equation, and then you start solving for it. Okay, so here what we need is we need the work input or the power input into the system. Okay, in this formulation that we are writing, we are basically writing for work output. Work output is equal to Qn plus m dot delta H plus the changes in the kinetic energy. Okay, so once these calculate the value of W out, we know that it's going to come out negative because work is not going out from the system, but it's coming into the system. So once we get the value for work output, we'll make that into a work input and write the power input to the compressor in kilowatt. Okay, so we don't have to worry about the sign for now. What we need to do is to be careful about what is the sign, right? And see whether it comes out positive or negative. Now we can go ahead and start plugging in the numbers. We got to see what is available to us, right? So Q dot CV or Q dot N is given as minus 180 kilojoule per minute. Okay, so this is provided to us. H1 and H2 can be obtained because we have the temperatures T1 and T2, and we are dealing with an ideal gas. So all we need is temperatures. V1 and V2 are provided to us. What is not given to us is the mass flow rate. So the question is, how do we determine the mass flow rate? Well, the answer is very simple. There's a formula for the mass flow rate. So mass flow rate is simply area times velocity divided by the specific volume, or you can say density times area times volume. Okay, these formulas were discussed in the beginning of chapter 4. So please go back and look through it if you missed out on that. All right, so here we are dealing with single inlet, single exit systems, right? So the mass flow rate at the inlet is exactly going to be equal to mass flow rate at the exit. Okay, and since we have area and velocity at the inlet, we can make use of this information and divide the area times velocity, which is the volume flow rate. You can divide it by the specific volume at state 1 to get the mass flow rate. So it's really important that if you're making use of area and velocity at state 1, you got to divide by the specific volume at state 1. You cannot, this cannot be A1 B1 by specific volume at state 2. No, it's not going to be equal, right? So mass flow rates are equal, volume flow rates are not. Okay, so that's something to remember. All right, so here, then the question is, how do we get this value for specific volume at state 1? Well, we're dealing with an ideal gas. So PV is equal to RT, or V is equal to RT by P. Okay, in this case, we need to use all the values at state 1. So we're talking about A1 V1 by RT1 by P1. Remember, temperature needs to be in Kelvin, pressure needs to be in kilopascal, and we have that information already given. So we can start plugging in the numbers: 0.1 meter square times 6 meter per second divided by the gas constant for air, 0.287, times temperature in Kelvin, 290, divided by 100 kilopascal. That's the pressure at the inlet. Okay, so when you plug in all these numbers, you get 0.72 kilogram per second. That's our mass flow rate. So now we need to get the enthalpies, enthalpy at state 1 and state 2, which we can easily get from table A22, which is for air, right? So at 290 Kelvin, the enthalpy is 290.16. At 450, it's 451.8. We get this directly from the table. So now we can just go ahead and plug in the numbers. So work output is equal to Q in, right, which is basically minus 180 kilojoule per minute. And since it's 1 kilojoule per minute, we need to convert this into kilojoule per second. So Qn is minus 180 by 60 kilojoule per second plus m dot times h1 minus h2 plus v2, sorry, plus v1 minus v2 square by 2, right? This is simply what we had here. H1 minus h2 plus v1 square minus v2 square by 2, nothing else. So remember to divide by 1000 when you're dealing with velocities to convert joule per kilogram to kilojoule per kilogram. So when you plug in the numbers, this is what you get. Again, you can see that the change in enthalpy is 161.64. The contribution of velocity kinetic energy is 0.02. It's very, very small. Even if you neglect it, it's not going to change the power output. Okay, so this is the sorry, it's not going to change the power input. So this is the power input, the power output as per the formula, and the power output, of course, comes out to be negative because there's no power output in a compressor. A compressor produces it requires some work input or a power input to produce the pressure rise that we need. Okay, so therefore we can say that since workout is negative 119.4, it basically means that work is coming, power is entering into the system and work is entering the system. So the work in should be equal to 119.4 kilowatt, or the rate of power input should be equal to 119.4. Okay, so that's it for now. I'll continue more in the next next video. Thank you.